Good morning, everyone. It is a great pleasure to welcome Francisco today, Francisco Javier Fernandez Alonso. And it's always a pleasure to have young scientists presenting their research at the Netpore webinar sessions. And so I will take the opportunity to give you this message of contacting me if you're a young scientist in your PhD or postdoc training. Please don't hesitate to contact Luca or myself if you want to participate to the webinars. It's always a great pleasure. And today, our young scientist then is Francisco. He's a PhD student currently at the Department of Applied Physics and Center for Microanalysis of Materials at the Autonomous University of Madrid. Francisco holds a degree in physics from the same University of Madrid and a master's degree in advanced materials, nanotechnology, and photonics. He is currently beneficiary of a competitive national predoctoral contract for university professor training, and his doctoral thesis is on the study of nanostructure oxides for functional applications. And today, Francisco will be talking about nanostructure metal oxides for environmental applications. Please, Francisco, please go on.
So, thank you very much, Frederic, for the very kind introduction. My name is Fran Fernandez Alonso. I come from the Autonomous University of Madrid in Spain. And today I'm going to talk about some works that have to do with the research we do in our group about nanostructure metal oxide for environmental and also some biomedical applications. So first of all, I would like to briefly introduce my institution. I come from the Autonomous University of Madrid in Spain. This is our campus. It's quite beautiful from my point of view. We are, according with several rankings, one of the best universities in Spain, and we offer several undergraduate and graduate studies in science, physics, chemistry, chemical engineering, etc. So in this talk, I'm going to split the talk in three parts. I will talk about three different works. The first one, I will talk about a work in which we have synthesized hydrogenated titanium oxide nanotubes synthesized by microwave plasma annealing for enhanced photocatalytic applications. Then we'll move to a second work in which we have worked in the understanding of the synergistic effects of titanium and tin co-doping on the photoelectrochemical water splitting of hematite nanowires. And finally, I will talk about the synthesis of magnetic nanoparticles using rapid microwave plasma hydrogenation for biomedical applications. So, starting with the first work, hydrogenated titanium oxide nanotubes synthesized by microwave plasma annealing for enhanced photocatalytic applications. First of all, what are photocatalytic materials and why it's important to do research in this topic? Well, maybe all of we know, but photocatalytic materials are materials in which, by absorbing photons with enough energy, they can notably enhance certain chemical reactions, essentially by starting free radical mechanisms. They have multiple applications that go from dye degradation, hydrogen production, from water splitting, bacterial disinfection, conversion of pollutants into fuels, air and water purification, or even cancer therapy. So in this first work, what we did is to synthesize titanium oxide nanostructures, hydrogenated, and as a proof of concept, we applied them in the photodegradation of acetaminophen, for water purification. So why did we decide to work with titanium oxide? Titanium oxide is one of the most used photocatalytic materials and most studied, mainly because it has a very high photocatalytic activity under ultraviolet illumination. And this is mainly because it has a very high ability to generate reactive oxygen species that can contribute to the photodegradation of organic pollutants in water. Also, it's non-toxic. It's it's very stable, chemical stable, and also it's very environmentally safe. And also is quite cheap compared to other photocatalytic materials and quite abundant. However, it also has some disadvantages. The main one is that it has a very wide band gap, about 3.2 electron volts for an task. And this makes titanium oxide only suitable for photocatalytic applications under ultraviolet illumination. And ultraviolet light only represents about 5% of the solar spectrum. So this is quite far from optimum. However, it has been reported that by introducing defects or mid-band states that can be associated with oxygen vacancies, titanium 3 plus centers, hydrogen doping, etc., we can, by introducing these mid-band states, allow the absorption of visible light and in this way enhance the photocatalytic performance under solar light. Also, titanium oxide has a quite fast electron-hole recombination. Again, it has been reported that by doping or by introducing defect sites into the structure, we can introduce electron traps that can allow to or can help to reduce recombination and in this way enhance the photocatalytic performance, since less electron hole pairs are going to recombine before participating in the photocatalytic reaction. So the objectives of this work were to synthesize titanium oxide nanostructures with high specific surface area nanotubes in order to have the greater photocatalytic efficiency as possible, and also hydrogenated. On the one hand, to try to enhance the visible light absorption and also to try to reduce electron hole pair recombination and in this way enhance the photocatalytic efficiency. To prepare the nanotubes, we followed a very well-known procedure and that it has been reported by a lot of authors, in which we anodize a titanium foil. In this case, we applied 60 volts for 20 hours in an electrolyte containing ammonium fluoride, water, and ethylene glycol. After that, we obtain a titanium oxide membrane. However, it's amorphous at this point. And to have a good photocatalytic efficiency, it's convenient for the material to be crystalline. So after the anodization, we performed a thermal annealing process at 400 degrees for 2 hours. And after this, we have anodized titanium oxide. At this point, we have crystalline titanium oxide. However, we have like black titanium oxide. This titanium oxide is not suitable for visible light absorption, since the band gap is about 3 electron volts. So in order to introduce these defects, to convert it to black or gray titanium oxide, we followed two approaches. The first one is a very a more used method that consists of a thermal annealing in a reductive atmosphere containing a mixture of argon and hydrogen. Here we have the furnace we use for that purpose, and we introduced a mixture of hydrogen and argon in a 1:2 proportion and proceed with the reduction for 3 hours at 400 degrees. And this method has the main disadvantage that it takes a lot of time, because you have to make vacuum, then introduce an inert atmosphere, then introduce argon and hydrogen, heat, etc. So it takes 6 or 7 hours. So it is not very suitable for industrial applications. And as an alternative, what we did is designing this method that consists of a microwave plasma annealing. It's like a microwave machine that, similar to the ones we have at home. We make vacuum, we introduce a mixture of hydrogen and argon, and by applying the microwave, we induce a plasma. And in this case, we can significantly reduce the time it takes to reduce the sample, since instead of 3 hours, we only have to perform 20 cycles of about 30 seconds. Here we have some characterization of the nanostructures we synthesize. Before hydrogenation, we have a very well-defined template of titanium oxide nanotubes of about 90 nanometers of length, of diameter, sorry, and about 100 microns of height. When we apply the thermal annealing, we see how the morphology is more or less conserved. We introduce some defects, but the morphology is more or less preserved. And when we apply the microwave plasma annealing, we see how the surface is like melting a little bit, but again, the structure or the periodicity is more or less preserved. And here we can see how before hydrogenation, this is the sample taken anodized, and after applying the thermal annealing at 400 degrees, we have white titanium oxide, since this has not been reduced. And after applying the microwave plasma annealing, we see how the sample presents a dark gray color that is indicative of its ability to absorb light in the visible range. So we performed some photocatalytic experiments. For that, as I told before, we used acetaminophen as a proof of concept, and we prepared a dissolution, 5 parts per million. I took 100 milliliters of that solution and introduced 9 milligrams of our catalyst. We illuminated the sample with a solar simulator, and we took several samples in order to measure the quantity or the content of acetaminophen with time. We did the measurements by HPLC, and by knowing that the reaction is expected to follow first order kinetic, we can determine the apparent constant of reaction by having the evolution of the concentration with time. Here we have the results of the photodegradation experiments for different concentration of hydrogen for the microwave plasma hydrogenation procedure. We see how by introducing this hydrogenation, we can enhance the photocatalytic efficiency more or less by a factor of 2. However, we see that we need a minimum quantity of hydrogen for this improvement to be significant, since we see that when we introduce about 1% of hydrogen, the improvement is low. However, when we introduce a hydrogen quantity of more than 5%, we see that the improvement in the photocatalytic efficiency is it saturates. When you introduce more than 5% of hydrogen, the results you obtain are more or less similar. We also compared the samples prepared by the microwave plasma annealing with samples prepared by the thermal annealing process with a similar amount of hydrogen. And we see that the results are more or less comparable. So the efficiency of the microwave plasma hydrogenation is similar to that obtained by the thermal treatments with a similar hydrogen concentration, which means that this microwave plasma annealing process can be used with good results. We performed some microstructural characterization of the photocatalyst, and we observed how after the annealing process, we have an anaphase phase, more or less with a random orientation, with a similar peak intensity of that of anaphase. However, when we reduce by applying the thermal reduction process or by applying the microwave plasma, we see a reduction in the intensity of the 101 peak. This is expected to increase the photocatalytic efficiency, since the 101 phase set is less reactive than the 001 phase. So we have to perform more characterization on this photocatalyst. This is a work in progress. However, we can conclude that by applying this microwave plasma annealing procedure, we can obtain results similar to those obtained by applying a thermal annealing process. And this method is much more cheaper and faster than the thermal annealing procedure. And well, as I told and I showed before, the photodegradation efficiency can be increased by more or less a factor of 2 when the sample is hydrogenated. So we have some work in progress. We would like to better understand the mechanism of photocatalysis. For that, we want to perform X-ray absorption spectroscopy experiments and XPS experiments. Since XPS is a much more surface sensitive technique, we can see if these defects are on surface. We expect so, but by also performing X-ray absorption spectroscopy, we can see if these defects are only on surface or if they are also in bulk, since the X-ray absorption spectroscopy is a technique that is more bulk sensitive. And also we would like to perform some ERDA experiments to see if hydrogen is being incorporated into the structure, or if these defects are only because of the creation of oxygen vacancies, titanium 3 plus centers, etc. And also we would like to investigate if hydrogenation and other techniques used to improve photocatalytic efficiencies, such as a noble metal loading, can work synergistically. So now we will move to the second work, that is about understanding the synergistic effects of titanium and tin co-doping on the photoelectrochemical water splitting of hematite and nanowires. In this case, of course, solar energy is a very clean, sustainable, and abundant energy source. If we were able only to convert 0.01% of the solar energy we receive from the sun each year to electricity, we would be able to satisfy all the need for energy of the planet. And also, it's a very clean and sustainable energy source, so the investigation in this topic is justified. There are several ways to produce electricity or fuel from solar light. The most natural way, let's say like that, is the photosynthesis process that takes part in the leaves of the plants. And in this case, solar light in conjunction with carbon dioxide and water is used to produce sugar, that is like the fuel of the plants, and oxygen. Also, we have photovoltaic devices that consist of a p-n junction device, and when they are illuminated, a current can flow. However, they have the main disadvantage that this electricity can't be stored without using additional instrumentation such as batteries or supercapacitors. So PEC cells are an alternative to photovoltaic devices, in which, again, when we illuminate, we create a photocurrent, and we can produce chemical energy in the form of hydrogen molecules that can be stored and used when necessary. So in this case, what we did is working with hematite. Hematite photoanodes are very well studied because they have a very long-term stability. They are also quite cheap. The band gap is is narrow, about 2 electron volts, which means that can absorb about 40% of the solar spectrum. And also the maximum solar to hydrogen conversion efficiency is about 12.9%, which is quite good. However, it has some disadvantages. For example, the carrier's mobility is quite low. The conductivity of hematite in its pristine form is also quite low. And also it has a very short hole diffusion length, which makes that an important part of the photogenerated electron holes pair are going to recombine before participating in the water splitting process. So the objectives of this work were to synthesize hematite photoanodes with nanowire morphology to try to have the highest specific surface area as possible. Doped with titanium to see the effect of titanium doping into the photoelectrochemical properties. And also we studied the application of a high temperature annealing step. On the one hand, to see the effect of the increase in crystallinity, and also to see if we are able to dope the structure with tin, since the substrate is fluorine doped tin oxide, and we wanted to see if by applying this high temperature annealing we can diffuse the tin to the hematite. So for the synthesis, we followed a hydrothermal method. We used as precursors iron chloride, sodium nitrate, and chlorhydric acid. And for the samples containing titanium, we used also titanium isopropoxide. The hydrothermal procedure took 13 hours at 95 degrees. And after that, we followed two different approaches. The first one consisted of a single annealing step at 600 degrees for 3 hours, and the second approach consisted of a 550 degrees for 3 hours, plus a high temperature annealing step of 800 degrees for 20 minutes. Here we have the morphological characterization of the photoanodes. We see how just after the annealing, just after the hydrothermal synthesis, the nanowires are more or less formed. And we see how when we apply the annealing, when we apply the high temperature annealing step, in both cases, we see an increase in the diameter of the nanowires of about 50%, which can mean that some nanowires are melting because of the high temperature annealing, and in this way creating nanowires with a larger diameter. We also perform some microstructural characterization. We see how all the samples present a preferential orientation in the 110 direction. This is expected to enhance the photochemical efficiency, since the 001 basal plane is about 4 orders of magnitude. It has a conductivity about 4 orders of magnitude higher than direction perpendicular to it. However, we see that the preferential orientation is greater in samples that are subjected to annealing at 800 degrees compared to the ones that are only subjected to the low temperature annealing. And also we see that this effect is greater in undoped samples compared to titanium doped samples. We perform some Rietveld refinement, and we see how the samples that are not doped with titanium present like similar lattice parameters with both annealing approaches. When we introduce the titanium, we see that when we apply the high temperature annealing, the lattice parameters are reduced. This can mean that when the titanium may be incorporated into the structure on surface during the hydrothermal synthesis, and it needs the high temperature annealing step to go towards bulk. And in this way, we only observe this reduction in the lattice parameter when we apply the high temperature annealing. We also perform some estimation of the crystallite size and microstrain by applying the Williamson-Hall method, and we can see how the samples that are annealed at high temperature present a higher crystallite size. This is expected. and also the samples that are doped with titanium present a slightly smaller crystalline size, and microstrain is minimal in all cases and not very significant. We perform some in-depth compositional characterization by RVS, and we can see how the amount of tin on surface is greater for the sample that contains that is non-doped and annealed at 800 degrees. This can be due to a greater diffusion of tin in this sample, but also because of a greater roughness. If we have a greater roughness, we can have part of the samples that have a lower atomic thickness of iron, and in this way, when you apply RVS, you see more tin on surface. In the case of titanium dope sample, we see a similar distribution of iron and tin. However, we see that the sample that is annealed at 800 degrees presents a slightly lower amount of titanium on surface, but more titanium on bulk. And this may be consistent with what I said before, that maybe the titanium is being incorporated on surface during the hydrothermal synthesis, but it needs the high temperature annealing to be diffused towards bulk. Also, by scanning electron microscopy in cross-section, we can estimate the physical thickness, let's say like that, like the nanometric thickness of the photoanodes. And by RVS, we can estimate the atomic thickness of the photoanodes. We see how the samples that are doped with titanium present a higher nanometric thickness. However, by RVS, we see that these samples present a lower atomic thickness. And this means that we have like more material in the case of titanium doped samples, we have less material, less atoms of iron in more nanometers of sample. And this can be an indicative of greater porosity. Of course, to have a good result of porosity, you have to apply a bed or something, but this can be an indicative that we have like less material in more nanometers, let's say like that. We also perform some photoelectrochemical impedance spectrometry characterization, and we can see a reduction in the bulk resistance when we apply the high temperature annealing step. And we also see a reduction in the bulk resistance when we apply the titanium doping. And in the case of the resistance on the surface state, we see also a reduction with titanium doping that can mean that the presence of titanium 4 plus ions at the surface can prevent positive charge accumulation at the hematite surface and decrease the surface recombination of the trapped electrons with holes from the valence band. We perform some photoelectrochemical performance. We see how by doping with titanium and applying the low temperature annealing step, the photocurrent can be increased from 0.02 to 0.64 milliwatts per centimeter square. And if we combine this with the high temperature annealing step, we double the photocurrent to 1.27 milliwatts per centimeter square. We also check the stability for 2 hours, and we observe how the photocurrent is more or less stable for 2 hours, and measure IPC, and we see how the sample that contains titanium and the high temperature annealing presents the greater value of IPC. So the conclusions of this second work are that titanium doped hematite nanowires can be synthesized by hydrothermal synthesis. By doping with titanium, we can increase the photocurrent from 0.02 to 0.63 milliwatts per centimeter square. This can be attributed to the passivation of surface states on hematite and the improvement in bulk conductivity. And also by doping with tin by annealing at high temperature, we can double the photocurrent to 1.27 milliwatts per centimeter square. And this can be attributed to an enhancement in bulk conductivity and also an increased crystallinity. So now we are going to move to the last work I wanted to present today. about the synthesis of magnetic nanoparticles using rapid microwave plasma hydrogenation for biomedical applications. Well, magnetic nanoparticles have multiple applications that go from diagnosis, for example, as new magnetic resonance imaging contrast agent, biomolecule separation, but also for therapeutic applications, for example, in magnetic hyperthermia, drug delivery, or cellular magnetic stimulation. For biomedical applications, it's desirable to have non-spherical nanoparticles, since these nanoparticles are more likely to contact cells, since they have more contact points, and also they are expected to have an increased circulation. And related to magnetic properties, it's desirable to have a high saturation magnetization, low coercitivity, low remanence, and a monodisperse distribution. So in this case, what we do is we synthesize hematite nanoparticles by an hydrothermal synthesis. We use as a precursors iron chloride and ammonium phosphate. And by modifying the ratio of iron chloride and ammonium phosphate, we can determine the size and the shape of the nanoparticles. Here we have some characterization, morphological characterization of the nanoparticle we synthesize. This has been published in ACS, Applied Materials and Interfaces, by the group. We see that if we don't add any ammonium phosphate, we obtain nanoparticles of about 400 nanometers with a cuboidal shape. If we introduce some ammonium phosphate, we see that the morphology is changed to like more an ellipsis nanoparticles with about 1 micron of the longer axis and 700 nanometers for the shorter axis. And if we double the ammonium phosphate concentration, we see that the morphology changes and we have like more needles. We have like a reduction of the short axis length. By XRD, we can see that in all cases we have hematite of about 60 nanometers of crystallite size. And again, this is hematite. We want to convert them to magnetite. So we follow two approaches in the group. The first, they are the similar we follow for the black titanium synthesis. The most or the first method that is the most reported one is the thermal reduction annealing process in this furnace. In this case, we do the procedure at 480 degrees for 5 hours in a mixture of hydrogen and argon. And we see that the morphology don't change a lot. We see like a bit of reduction of the shape, and we see visually like we are introducing some pores into the nanoparticles. However, when we apply a bed, we see that the bed surface area is decreasing notably after thermal reduction, because we see we also have a modification of the pore diameter, and although we see like a greater roundness in the nanoparticles, when we apply bed, the bed surface area is decreasing when we apply the reduction annealing. We perform some X-ray diffraction characterization. We can see how for the nanocubes and the nanoneedles we have almost all the sample converted into iron. However, the nanoellipsis is a mixture of iron and magnetite. This can be due to a lower hydrogenation because of its larger dimensions and roundness. So maybe hydrogen can't penetrate towards the bulk of the nanoparticles. And also, we perform some magnetic characterization, and we see how the magnetization results are close to 200 mu grams. again, we obtain like a bit lower saturation magnetization for the nanolipsis, which is consistent with the lower concentration of iron in the nanoparticles. So as an alternative to this thermal annealing, we also tried to apply the microwave plasma annealing. And what we see, this is a work in progress. We obtain at this point lower magnetizations. We are able to obtain more or less 40 mgrams. We have tried to use different pressures of the reactor, and we see how when we reduce the pressure of the in microwave chamber, we obtain a greater magnetization, which can be because we have less ions into the plasma, into the atmosphere, and in this way we are increasing the mean free path of the ions. And we see as expected that by increasing the hydrogen concentration, we can increase the saturation magnetization of the nanoparticles, obtaining for a 40% of hydrogen at 0.15 millibars, about 40 mgrams, as we can see here. We are trying to apply these nanoparticles for some biomedical applications, in this way cellular magnetic stimulation. For that, we performed some experiments that were performed with glial cells. We applied a magnetic field of about 131 millitesla for 1 hour, and we tested two frequencies, the high one about 0.1 hertz and a lower one of 0.01 hertz. For each frequency, we tested for concentration of nanoparticles, and we tested the thermally reduced nanoliths and nanocubes, as well as the microwave plasma reduced nanocubes. And we measure cell viability for 24 and 48 hours after stimulation. Here we have the results, and we can see that the microwave plasma annealed nanocubes present the best viabilities at concentrations lower than 100 micrograms per milliliter for 48 hours viability, and similar results can be obtained for low and high frequencies. So to conclude this third work, we have synthesized hematite nanoparticles by using a hydrothermal method. By changing the molar ratio between the precursors, the shape and size of the nanoparticles can be modified. Magnetic nanoparticles have been obtained by reducing hematite nanoparticles using a thermal process in a reductive atmosphere, and saturation magnetizations of about 203 mgrams have been achieved. By using microwave plasma hydrogenation, nanoparticles with a saturation magnetization of up to 41 mgrams can be obtained. We are, or because of the color of the nanoparticles that is like metallic, we think that only the surface of the sample is being reduced, with hematite remaining in bulk. And also the applicability of the synthesized nanoparticles in cellular magnetic stimulation has been demonstrated. We have some work in progress. We would like to study whether these nanoparticles, the nanoparticle reduced by microwave plasma, is in fact a core cell structure. We would like to perform some yields characterization to check this, and also to try to study the applicability of higher proportions of hydrogen in the plasma, as well as lower pressures, to see if we are able to enhance the saturation magnetization. And also we would like to try to functionalize the nanoparticles to try to improve their biocompatibility. And in 2 minutes, I would like to present the Center for Microanalysis of Materials. That it's a institute that is as part of the Autonomous University of Madrid. We have a 5 megavolts terminal voltage tandem accelerator with 6 beamlines. a standard external microbeam, ERDA time of flight, internal microbeam, implantation and nuclear beamline. This is a public installation, so any a researcher that is interested can submit a proposal that is evaluated and can come to the institute to use our instrumentation. We have several techniques, RBS, ERDA, PIXI, etc. I'm going to present some results that can be obtained there. For example, well, this is an RBS spectrum of the hematite nanoparticles I showed before in the second work. And in the internal microbeam, we can do RBS or PIXI with micrometric resolution to try to do a map of the different elements of the sample. This is another example, for example, of a Cooper mesh. We also can do STEAM, scanning transmission ion microscopy. For example, this is an example of an artery, and we can see the concentration of or the different density in each part of the sample. And here, finally, we have an example of further time of flight in which we can be used to characterize light elements. So thank you very much for your attention, and I'm open for questions. Thank you very much.
Thank you very much, Francisco, for this very great and clear presentation of all the topic. It's so much work you've already accomplished in your PhD, and it's very, very interesting and different point of view. So please don't hesitate to ask question if you have. You can raise your hand or just start speaking. So many topics. So I have a few questions. We can start with my question. The first one is a quite general question, and the first part of your talk on the photocatalytic materials that you have designed, and it seems very interesting and promising to use this doped hematite with TiO2. And I was wondering, in this case, if you have a opportunity to upscale this production, or if it's a laboratory.
The titanium dioxide nanotubes.
Yes, with the one you use. It's the second part of your talk.
Okay.
In the second part, with the hematite, the doped hematite.
In our lab, it's small samples.
Okay.
It can be scale up. Again, when we do photocurrent measurements, when you use a larger area, you obtain worse results. It's quite scaling up these techniques. It's not easy.
It's not
but
easy.
It has been reported. There are works about scaling up. Because for industrial applications, of course, you don't need 1 centimeter square. You need like greater. In our lab, we don't do, but I think it could be possible.
It is doable, and it's some
Yes.
optimization research. It's pretty common with this in this oxide or semiconductors, porous semiconductor generation, or small materials by electrochemical techniques sometimes. So that's why I was curious, because the system has very improved properties and seems very interesting. So I was wondering where you could push this forward in terms of upscaling. Another comment, of course, now is on the last part of your talk and concerning the biomedical application. Could you please go back to the very last slides where you show the demonstration of these nanoparticles, magnetic particles? Yes. So what is the here, because it went quite quick for me, and what is your conclusion on the cellular stimulation using this?
Well, this is We in the part of the group, I don't do that, but for example, have applications in proton therapy. So there is like a technique. I'm not an expert in that,
Yeah.
but cellular magnetic stimulation is like you try to make the cells happy. Let's say
Okay.
like that, and to try to increase the viability.
Okay.
And
So
in
what
this
you're,
case,
yeah,
well, these nanoparticles are not functionalized.
yes.
That's why the control groups have viabilities that are lower than 100%. They are toxic. Okay,
Yep.
for this to have a real application, we would need to functionalize and try to make the control group have the greatest viability as possible.
Okay.
But we see that when we apply this magnetic field, we have an increase in the viability of the cells.
Okay.
And that's like the application. But of course, this is work in progress, because if you see, for example, the error bars are very high. We have to do more experiments.
Sure.
It could be ideal to functionalize the nanoparticles to try to have more clear results or more applicable results.
Okay. That's interesting. I was wondering because you went quick, and that's the point I missed. We usually, when you look at cell viability in bio, whatever, it's always to kill cells because of cancer or something. And so I missed the point, and you increase viability. So that's why
Yes.
I went back to you on this point to make sure that I get the point, and it's very clear. So what happened in this case is just because this concentration is toxic to the cell, I guess. That's why you have this poor cell viability initially, I guess.
For the control group, yes. I
Yeah.
mean, you have to functionalize with a polymer or something to try to make them non-toxic.
Okay. Did you
Uh,
already you mentioned that in your perspective, the functionalization? You have started on this, or you have
and
ideas already?
we are in progress. We
Okay.
have there is another PhD student in the group that is working on that, and
Okay.
also there is a master student that is working on that. We are in progress.
Okay, still exploring. Okay. Thank you
Yes.
very much, Francisco. We still have time for question. Please don't hesitate again to raise your hand or just to talk to Francisco. It's very interesting work, a lot of diversity with material science and applications in very relevant topics in environment, health. It's very interesting. No, I think may not have more question. Okay, so I have no more question myself. Again, thank you very much, Francisco, for the presentation of your work. It's very interesting. We wish you a nice continuation and progress, and look forward to hearing you in a few months or years when you have, wrap up your story, and it's very interesting again. And so again, if you yourself are a young scientist, or if you have young scientists in your group that you believe could present some part of their work here, please don't hesitate to register or to contact me. You're welcome. This counts also as an invited talk. It's very good for your resume, and it's very interesting to present what you're doing, and eventually meet other scientists, and have a chance to be known. Okay, so it was very nice. Thanks again, Francisco. Thank you all for your participation, and wish you a very, very good day. See you in a month. Thanks. Thank you very much.
Thank you very much. Bye.
You're welcome. Bye-bye.
Bye.
Ciao, ciao.
Francisco. Ciao, Luca. It was good seeing you. Thank you.